68. So let's start with two very small exercises and then we try to answer more general question. So first part of the exercise. So let's show that the quotient by A and the tensor by itself. Let's use the notation like this. Prove that this is the quotient by itself. In particular, this is not 0. So actually this is easy. We've already proved that. Exercise 65 or 66, I'm not sure. Maybe 65. Actually, we have proved that at the Z module. So here at the Z module. Actually, we have proved this is this, right? So let's continue. But now, if I take Q quotient by Z, and then a tensor with itself, I claim this is 0. So notice, actually you can think of it as a submodule 1 over A of Z quotient by Z. And this is not 0 because this is basically isomorphic to this, right? And so here is the point, prove this. So one way to prove this is, recall that exercise 66 or 65 maybe, not sure. We have to say that the tensor product of our modules is 0 if and only if any bilinear map from Mn to some R module P is 0. Right? And so let's say, look at this bilinear map. Suppose you have some whatever element S over T, then M over N, and then you map it to S over T M over N. We have to prove whatever element like this is always 0. Right, but notice this is, the only thing we use is Z bilinear map. And so this is the same as N times 1 over N times S over T M over N, and then you could move this N freely outside because this is always still inside Q quotient, no problem. And when you move it outside and then you use bilinearity, send it to the second position, you hence got this, right? And this is integer in Z, and so this is 0 in Q quotient by Z, and so this is 0. Okay, so after these two small exercises, let's ask a more general question. Or let's be more direct. Our argument is that the difference between this first example and the second example is that this is a finitely generated Z module. Well, this is not finitely generated Z module. So our statement is, if M is a non-zero finitely generated R module, then M O times K is not 0 for all K. So the proof actually is very tricky in my sense, but it works. Okay, so let's, because this is finally generated, suppose we write M as R tensor E1 plus tensor E2 plus etc. tensor ED with D the minimal possible integer. And then we rewrite it as n plus times ed. Basically, we collect the first d minus 1 term and call it n. And then after we write like this, let's notice that because this is the minimum possible, and so our tensor ed is not in n, in particular ed is not in n, right? So we define ideal such that times ed is contained in n, so obviously 1 is not there, and one checks this is ideal because addition is there and it's closed under multiplication because n is a submodule. This is a proper ideal. Now what we do is that we want to construct a bilinear map from M of k to R quotient I. So this is the very constructive part. So observation is that any element can be written into element in n plus some r times ed with r unique up to modulo the ideal I, proper ideal. And then this is kind of unique, and then we could, for whatever element, m1, m2, so we can all write it into that form. So let's say m1, m2, mk, let's write it into the form n1 plus r1 ed, n2 plus r2 ed, nk plus rk ed, and then we map it to, so we only claim, it doesn't claim the uniqueness of the ni, we claim the uniqueness of ri modulo I, so we map it to this. So first, let's check why this is the case. Say observe or claim. Let's check the claim. So if you have n plus r1 ed equals n, let's say n1, n2 plus r2 ed, then this implies ny minus n2 plus ed times r1 minus r2 equals 0. In other words, r minus n2 minus n1. So this is again n, and so you have find the element of r, multiply ed side n. This implies r1 minus r2 is in I. Okay, And so we have proved our claim. Now we look at this map. This is a bilinear map, a multilinear map. Basically, when you multiply each component by R, it contributes R on the right hand side, and it's R linear. And so this induces tensor product of M to our quotient line. One tensor M2 MK to corresponding R1, R2, RK. We want to show this is non-zero. If it's totally zero, then all the image must be zero, right? So in particular, let's take R1 equals 1, R2 equals 1, RK equals 1, and so this is coming back to there exists some element here map A to 1. And so this is our linear map. Let's call this X. So fx equals 1 implies x is not 0, implies not 0. This is very tricky. Kind of you claim to show this is non-zero. I'm going to construct a, so to show this is not 0, it suffices to construct a f R linear map, right? To find our linear map such that some element is not 0, because 0, our linear map 0 to 0. If you could construct our linear map, that is as non-zero image, then it's okay. And then it breaks to construct a bilinear or multilinear map such that fx is not 0, right? I would say this is very tricky in my sense.